So now we are going to discuss about haloarenes. What is haloarenes and how can we prepare these haloarenes? So as you can see, if you just react chlorine, if you want a chlorobenzene, okay, if you just react a benzene ring with chlorine in presence of FeCl3, which we know that this is a Lewis acid, in presence of 310 to 320 Kelvin temperature, then we would get chlorobenzene. Okay. Now, how this reaction occurs? What is the mechanism? Okay. So first see, there are three steps. Okay. First is generation of electrophile. So as you can see, FeCl3 is in Lewis acid, so it reacts with chlorine and it takes up one chlorine from this Cl2. So what happens is we get FeCl4 minus and Cl plus. As we know, chlorine is nothing but Cl and Cl. Okay. So FeCl3 is a very good electron acceptor. So it accepts Cl minus. If you break it as Cl minus and Cl plus, just think about it. If you can form Cl minus and Cl plus from here, then if Cl minus would get attached with Fe, then we would get FeCl4 and Cl plus. Okay. Now as you know, this Cl-Cl bond should undergo homolytic cleavage. But FeCl3 is the deciding parameter here. So this is the driving force which makes this Cl-Cl bond break into Cl minus and Cl plus. Okay. Now, this is how an electrophile is generated. Why we call it electrophile? Because this is electrophilic, like it wants electron. Now, the second part is formation of carbocation intermediate. So, as you can see, the benzene ring reacts with this Cl plus, this electrophile. So as you can see, the pi bond is nothing but some dense, like this is the electron cloud, right? So this electron just attacks this Cl plus, which is an electrophile. So after that, what we get is we get this type of structure. So as there are the lackage of electrons from this bond is involving itself to react with Cl, so there you can find a plus charge, right? After that, this can undergo these three types of resonance structure. So here you can see that this plus charge, if you just, this bond comes here, then we would get this resonating structure. So this bond is coming here. Then we are getting this resonating structure. After that, what happens is this bond comes here. So we will get this resonating structure. So thus we can have this resonance hybrid, right? Okay. Now we can say that formation of carbocation intermediate. So this is the carbocation intermediate, right? The plus charge is delocalized in the whole benzene ring. Now the last part is loss of a proton from the carbocation. Now what happens is, as you can see, these three forms are not stable at all. They want to regain their energy. As you can see, the benzene is an aromatic compound and it have a high stability, a very low energy and a high stability. So this compound wants to go back to that structure. So for that, it releases this proton. Like this bond breaks and this proton gets released. And now this proton just takes one Cl minus from here to give HCl, FeCl3 and chlorobenzene. So this is the mechanism of formation of any type of electrophilic reaction. This is the general mechanism for any type of electrophilic reactions as well. Okay. So now, if you add some excess chlorine in this type of reactions, what would happen? In presence of FeCl3, definitely, because if you want to do some replacement in this ring, definitely you need to add some FeCl3 because you need to generate some electrophile. So if you use excess amount of chlorine, then definitely you would get an ortho product. Why? Because chlorine is an electron donating group. Okay, this is an electron donating group because for that reason, as we know from class 11 standard knowledge, that from that all the electron donating groups are ortho para orienting groups. So for that reason, we can say that it will give us an ortho product if you just give excess amount of chlorine, right? Now think about this. If you use toluene and if you give chlorine in the presence of FeCl3, what we would get is a ortho product as well as a para product, because toluene is nothing but an electron donating group. So this is an ortho para orienting. I have written it that electron donating groups are mostly ortho para orienting groups. So we would get ortho and para. Definitely para product is a major product. Okay, and boiling point, melting point, all the properties, physical properties are higher for this type of molecules, for para product, due to the symmetry. As you can see, the para product has a high symmetry, so the melting point of para product or boiling point, whatever the physical properties are, that would be greater with respect to the ortho product always. Now that was all about chlorination. Now come to iodination. Okay, if you want to do bromination here, just use Br2 FeBr3, then that would work. Now if you want to make iodination, then what would happen is just use I2 and HiO3 like you did previously. HNO3, HiO3, this type of oxidizing agent in the presence of I2. Iodine, when you are reacting with iodine, it doesn't need any Lewis acid here, because in the previous cases, Cl plus generation from Cl2 was not at all a simultaneous reaction. It needs someone to make this reaction happen. But in case of iodine is pretty much susceptible to this type of reaction. So you don't need someone to react with it. So we don't need any type of Lewis acid here. So a simple HiO3, an oxidizing agent, would do the work. Okay. Now, that was all about the substitution inside the ring. But now we would learn about sidechain hallucination. Now, if you want to substitute a hydrogen from the side chain, then what you have to do? So you can replace any hydrogen from the aromatic ring by applying Cl2 with some Lewis acid. But if you add this chlorine in presence of HNu and peroxide, then we would get a product in the side chain as a side chain substitution product, right? So I'll definitely come to the mechanism, but before that, let's look at another example. Right, you can see that there was CH2Cl. Okay, so CH2Cl we got from here, right? CH2Cl. So if you just add excess chlorine in this reactant, what would happen is that you would get CCl3. Okay, all the hydrogen here would get replaced by the chlorine, and we would get CCl3 in here. Okay. Now, if you have this type of molecules, previously here was CH3, now I have CH2CH3. Now, if you use chlorine and HNu, what would happen is the middle hydrogen would get substituted. The hydrogen of CH2 would get substituted, not the terminal one. The internal one would get substituted. Okay. So let's see what was the mechanism. So with the help of these two mechanisms, we are pretty much sure that this reaction proceeds via the radical mechanism. Let's see. So this is the reactant. After that, you are using HNu in presence of chlorine, right? So chlorine would undergo homolytic cleavage. We all know when we are using peroxide or we are using some amount of light, definitely every molecule that have same type of atoms. So in that case, it would break into radicals, right? Due to the presence of no electronegativity. Due to the no electronegativity difference in between them is there. So after that, what happens is there are two chlorine radicals. Among them, one chlorine radical would react with this hydrogen to form HCl and this carbon radical. So you can see there is a benzylic carbon radical. so which is very much stable, right? If that was terminal carbon, then this radical has no such stability. But in this case, this is a benzylic benzylic radical, so it can undergo resonance with the phenyl ring, right? You have learned it in class 11th. So here, this radical would react with chlorine radical to give us this type of reaction products. Okay, I think this is clear to all of you. Now, as you know, the formation of diazonium chloride is one of the most important reactions, because in aromatic compounds, diazonium chloride is nothing but the gateway to any products, to the formation of any products. So if you want to form any type of aromatic products, if you can just form diazonium salt of that aromatic compound, then you can convert that aromatic compound to any of the targeted materials. We will learn about them step by step. So before that, how to make diazonium chloride, how to make this thing. This is a very important reaction. Now as you can see, if you use NaNO2 plus HCl with aniline, then it would give us this diazonium salt. This is a very important thing, you know. So how would it form? What is the reaction mechanism? So NaNO2 and HCl together forms NaCl and HONO. This HONO is nothing but OH minus and NO plus. Now when aniline reacts with it, what happens is, you can see it here, NO plus reacts with aniline. This lone pair of nitrogen just hits the nitrogen of NO, and this bond breaks to give the electrons to oxygen, because oxygen is not at all stable in this state. It has plus charge. Now what happens is, you would find this structure, right? Now the water has a lone pair. Now with the help of this lone pair, water would attract this hydrogen. Okay, it would work as a base, and this lone pair would take this hydrogen. Okay, this lone pair would take this hydrogen. So what we get is, we would get one hydrogen less, because there was a plus charge, right? This system was not stable at all. So water takes up this hydrogen to make it neutral. And you can see there was H3O plus. But now the lone pair of oxygen takes up the hydrogen that water took from this nitrogen. Okay, because water is H3O plus now. It is also not stable. So after the taking of hydrogen, the structure of this molecule becomes this. Now water again comes and works as a base and takes up another hydrogen, and these bonds break into this, and this bond breaks and go to oxygen, giving us the result this. Now after that, this H3O plus again reacts, because this oxygen has a lone pair in its head. So this oxygen lone pair takes up this hydrogen, excess hydrogen from H3O plus to give OH2 plus. Now OH2 plus is a very good leaving group. Nitrogen, the lone pair of nitrogen pushes down, and this OH2 group gets out to give us this diazonium salt. Okay, I think you are very much clear about this mechanism, right? Okay. Sandmeyer reaction is one of the most important reaction of aromatic compounds. From this reaction, you can see that the diazonium salt of a benzene or any aromatic compound can be transformed into its halogen derivative. So you just need to add some copper chloride, Cu2Cl2, which is in dimer form, right, in presence of HCl. So you would get your desired product. And if you use Cu2Br2 in presence of HBr, then you would get the same halo substituted product, but this time it is bromine. This reaction was further modified by Gattermann, where you can see that he added, instead of Cu2Cl2, he added copper powder and HCl to increase the yield of the reaction. So you can see that this is the product we get. So what is the mechanism in this reaction? So as you can see, from the beginning, I am taking this benzene group as phenyl. It is also said that this is the phenyl group. So I am writing pH here, and N2 I am writing like this. Okay. After that, this reacts with Cu+. As you know, every metal undergoes single electron transfer mechanism, set mechanism. So Cu+ gives one electron, only one electron to this nitrogen, and this bond gets repelled, and this bond falls into N+. So what we get is this thing, where pH N, here is a lone pair, and in this N there was one lone pair and one single electron from copper. So copper 1 has become copper 2, right? Because one electron, he has donated one electron. Now in this situation, nitrogen N2, formation of N2 is very much favorable. So for that reason, this bond breaks to form N2. Like the one electron from this bond comes, and this radical together they makes N2 and pH radical. So you can see pH radical and N2. Now this pH radical reacts with CuCl2 to give us this type of mechanism. You can see that one bond breaks and copper and comes to the copper, and another electron of the bond is reacting with the pH to give us PHCl. Okay. Now that was all about chlorination and bromination. So if you want to do iodination, what would you do is just take this benzene diazonium chloride and react it with Ki. So it is as simple as that. That K with this potassium would react with this chlorine and would give us KCl, and this N2 would get out, because N2 plus N2 is a very good leaving group, and this iodine would take the place. So you can see this is the result. Okay. Now next is fluoroarenes. So we have learned about chloroarenes, bromoarenes, and if you want to make iodoarenes. So now the last part is fluoroarenes. So this type of reaction is called Schimann reaction. Okay. So if you take this diazonium chloride and react it with fluoroboric acid, so what would happen is, at 0 degree temperature, what would happen is it would transform itself to this, right? This HCl would get out. So it would form N2 plus Cl minus. Okay. Now after that, if you heat it, this N2 would get out, because this is a very good leaving group. Now BF4 minus is not at all stable, so it would give its fluorine to the benzene to make this BF3 and N2. So thus we can prepare chlorobenzene, bromobenzene, iodobenzene and fluorobenzene. Okay. So stay tuned for more videos.